Directions of the incident, reflected, and refracted rays at a smooth surface between two materials leads to the following three conclusions. The first one is the incident, reflected, refracted rays and the normal of the surface all lie in the same plane. So you see the incident light coming in red. It gets reflected partially at the surface in green, and then there's a refracted ray that travels into the medium. There are three angles, the incident, reflected, and refracted, that are all measured relative to the normal. Theta 1 being the incident angle, theta 1 prime being the reflected angle, and theta 2 being the refracted angle. The next two conclusions are derived as the law of reflection and the law of refraction. Let's go to those. Second conclusion, the angle of reflection is equal to the angle of incidence for all wavelengths for any pair of materials. Third conclusion, when monochromatic light of a single wavelength, is incident on a transparent medium, one of the rays will be refracted into the medium. This is known as Snell's law of reflection. Snell's law shows that the N, which is the index of refraction, more on this in a moment, that the index of refraction at 1 times the sine of the angle theta 1, where theta 1 is measured relative to the normal, is equal to N2 times sine of theta 2. Now, to interpret what Snell's law says here, I'm going to give an analogy. This analogy I call the lawnmower analogy. It explains why light is refracted at a boundary. The reason why light refracts or bends at a boundary is because there's a change in the speed of the light wave across a boundary. This analogy that I'm going to give you here is about a lawnmower that has one wheel on sidewalk and one wheel on grass. So looking at this image here, you see that you have a lawnmower where we're looking at it from the top view. On the upper side is the sidewalk, and on the bottom is the lawn, and the black line here represents the boundary between two materials. In optics, we call them mediums. So if I focus on the tire, the sidewalk represents a fast medium. That means that the tire will move faster on the sidewalk than on the lawn. As one pushes the lawnmower, the faster tire is going to move faster, the slower tire is going to move slower, and as a consequence, there's an overall bending of the lawnmower towards the slower medium. This bending by the lawnmower now has the analogy as light approaches a medium going from a faster to a slower. Refraction of light implies that there's a bending of the light ray. In summary, refraction of light is light changes speed as it enters a different transparent medium. Without going into the details of the index of refraction yet, the index of refraction is a material property of some transparent medium. We will talk about this more in a moment as to what it actually physically means. Now what I want to go do is that I want to go look at what happens when light interacts with the medium and the different types of refraction that can occur. For the moment, I'm going to assume that light always starts from medium N1. If that is the case, then there are going to be three cases. N1 equal to N2, N1 being less than N2 and N1 greater than N2. Picture-wise, I then start to draw the reflection, refraction, and incident rays as follows. If the incident ray goes from medium 1 to medium 2, and both of these are the same, the incident ray will not see any refraction and move along a straight line. On the other hand, if the medium N1 is less than N2, then an refraction occurs into medium 2. Picture-wise, you see that the angle moves towards the normal in this direction like this, and as it bends towards the normal, if I compare the magnitude of the angle theta 1 to the magnitude of theta 2, theta 1 will always be greater than theta 2. Our last possibility is when N1 is greater than N2. In this case, what you see in green here is that the ray is refracted away from the normal. And because it bends away from the normal, if I compare the angle of theta 1 to theta 2 here, which would be this guy in green right here, theta 2 will be greater than theta 1. Now what I want to do here is that I want to go to the PhET applet to show you this in detail. If you do a Google search here, you can get PhET applet on light refraction. So right now here is that I have a ray that's going perpendicular to the surface. So according to Snell's law, since the angle is at 90 degrees here, there will be the sine term will be 1, and therefore there will be no refraction. But since N1 and N2 are the same, as indicated by these two different indexes of refraction over here, if I move this at an angle here, what you're going to see here is that this ray continues to move in a straight line. So if I was to bring in here and measure my angle here, you could see that if I adjust this thing, the angle of the incident line from the normal in this case would read 60 degrees, and the angle of refraction relative to the normal is also 60 degrees. So now what I want to do here is that I want to change the index of refraction here. So now if I change the refraction, and if I increase the index of refraction of medium 2 here, and go all the way to water, you could see here that the index of refraction causes the ray to bend towards the normal. And as it bends towards the normal, the angle has now changed here. So if I look at the angle of incidence, which is 60, and I look at the angle of refraction here, which was earlier 60, you could see now that this angle is now smaller than the incident angle. And if I look at the numbers here, it looks like the angle of refraction in this case is 40 degrees. So I get the bending towards the normal when I go from a lower index to a higher index. Now, going back to our normal situation here, now I'm going to make this index of refraction higher, that is in medium 1. So if light starts off in water, let's say, what you're seeing here, as I move towards the index of refraction of water, you're seeing that the ray is doing what? It's bending away from the normal. So if I compare the angle again, you could see that the incident angle here is 60 still. But now if I look at this angle, you could see that this angle has grown more to sort of like 72 or 73 degrees here. So once again, you get this bending away from the normal when you go from a higher index of refraction to a lower index of refraction. Before moving on to the details of the index of refraction, I want to first do a demonstration.
All right, now this experiment is going to start with two containers, And this first container I'm going to fill up with water. Most of the way up. There we go. That's about right. And the second container I'm going to use corn oil. About the same amount. Now that we have these containers ready to go, the next step is I'm going to add an empty test tube to each one. We'll put one in the water first. We can see it. And I'm going to fill it up with water. And there it goes. And we can still see it very plainly. Now let's try one in the oil. Get one here. There it is. Put it in the oil. We can see that very plainly, but let's fill it up. And the test tube seems to disappear.
Question: why does the test tube disappear in corn oil but not in water? We can only see objects because of the differences in the index of refraction. So when I look at the test tube in water, the index of refraction of water and the glass tube don't match. As a consequence, the angle of refractions are different, and that allows our eyes to see the difference between the two materials. On the other hand, when I look at the test tube in the corn oil, what you find here is that both of these have roughly the same index of refraction. And because they have the same index of refraction, the rays are not bent and the object appears to disappear. The next thing that we need to talk about in detail is the index of refraction. The refractive index of an optical material plays a central role in optics. What we remember from what a light wave is, part of it is electric and part of it is magnetic. So when light interacts with the transparent medium, what the index of refraction is essentially the measurement of this interaction between light and the medium. In other words, the index of refraction is a measure of the electromagnetic characteristics of the material. That means when I look at the material characteristics, it could be broken down into two pieces. That is, the electricalness is known as the permittivity, the magneticness is permeability. However, for transparent materials in the optical frequency range, one can ignore the magnetic properties since that part of the material will not change. Therefore, the electricalness of the material is related to the index of refraction. The way the index of refraction is calculated is it's looking at the ratio-ness of the electricalness of the material of that to the vacuum, and this is related to the speed of light. That is, the index of refraction is n, which is equal to the electricalness and magneticness of a material over the electricalness and magneticness of the vacuum. And since the magneticness does not change as you cross that optical boundary, then I could cancel these out, and then it's the ratio of these two things. So it's the optical medium's electricalness over the vacuum electricalness, and this is what's equal to the speed of light divided by the apparent speed of light in the medium. So now I want to interpret what this index of refraction means in this situation. From the above equation, we can write the following thing here. The way we will rewrite the index of refraction here is that we'll write it in terms of the speed of light in the medium versus speed of light in a vacuum divided by the index of refraction. From the above equation, light appears to travel more slowly in a refractive index medium relative to the speed of light in a vacuum, because the index of refraction is greater than 1. That is, from this above equation here, you could see here that Vn, and if n is greater than or equal to 1, then what we say here is that Vn is a slower apparent speed of light in a refractive medium. Therefore, we interpret it the following way. So if the speed of light in the medium is Vn, then this is proportional to 1 over the index of refraction. A larger index of refraction implies there's more electrical interaction between the incident light and the medium. As a consequence, there's a lower apparent speed of light. On the other hand, if I have a smaller index of refraction, but definitely greater than 1, then there's less electrical interaction between the incident light and the medium. And as a consequence, there's a higher apparent speed of light. Here below in this table here, you see that I have different types of electrical mediums. I have an index of refraction, and then I look at the ratio of the speed of light to the index of refraction. All of the values for this table for the index of refraction is for monochromatic light of 589 nanometers. As we will talk about this thing briefly here in a moment, the index of refraction turns out to depend upon the frequency of the incident light. So what this table shows here is that it shows that as light goes from one medium into the next, the apparent speed of light slows down, and it's this slowing down process that causes the bending of the wave, that as we talked about with the lawnmower example. So let's look at a couple of examples. So why does light refract or bend when it goes from air into water? According to the index of refraction here, the speed of water to that of the speed of light is 75%. That means as light enters the water medium, it has slowed down by 25%, and that slowing down causes that wave to bend. Again, remember the lawnmower example. On the other hand, if we look at glass, you could see that the index of refraction is now going to slow down light by 33%. And that slowing of that wave allows that wave to bend more towards the normal. However, the index of refraction is more complicated than just the medium. It turns out that the index of refraction also depends not only on the medium, but the incident frequency of the light. In summary, the index of refraction depends on 1, medium type, and 2, the incident frequency of light. The index of refraction is only constant for a single frequency of light. On the other hand, if I have multiple frequencies of light, then the index of refraction changes. So this is the index of refraction for water. And you could see here that at low frequencies, the index of refraction is higher, which actually means that it's interacting more with the medium. At long wavelengths or low frequencies, the index of refraction means that it's interacting less with the electromagnetic waves. So when I look at this table for color here, you could see that red is around 650. So this would be the color red. And then if I go up to violet, which is around 380 or around 450, so this is violet light right there. Violet light has a higher index of refraction than red light. Therefore, violet light interacts more with the medium and therefore refracts more. Red light interacts less with the medium and therefore doesn't bend as much.